Hello, welcome to my 16463 project, speeding up 3D HDR reconstruction from noisy raw images. Neural radiance fields are a method that performs high-quality novel view synthesis from a collection of posed input images. Like most view synthesis methods, NERF traditionally uses post-processed low dynamic range images as input. These images have been modified by a lossy camera processing pipeline that smooths detail, clips highlights, and distorts the simple noise distribution of the raw sensor data. Recently, raw NERF modifies NERF to train directly on linear raw images, preserving the scene's full dynamic range and allowing view synthesis tasks to be performed on challenging HDR scenes, such as scenes from extremely noisy images captured in near darkness. Unfortunately, the algorithm is quite slow. Full optimization takes over 500,000 steps of optimization, which can take days on a single GPU. To speed up this process, we provide a faithful reimplementation of raw NERF that uses a multi-resolution hash encoding to speed up the optimization process. To describe the instant NGP implementation, input encodings have proven useful in neural networks, and NERF traditionally uses a frequency encoding, which uses a bunch of sine and cosine functions to help the neural network identify the location it's currently processing. Parametric encodings have also been used, and instant NGP is an example of the parametric encoding where, in addition to the standard weights of the NERF MLP, we have additional weights that are embedded in a hash table and optimized during reconstruction. NERF's MLP takes a 3D position XYZ and a 2D viewing direction as input, and it outputs a volumetric density and color. 3D rays are shot from the camera into the scene, and volume rendering is used to combine the colors and densities for many points sampled along each 3D ray. Our cache encoding helps with this. Each hash table is arranged into L levels, each with T feature vectors and each with dimensionality F. In our case, each hash table level independently stores features at the vertices of a different resolution grid. See the red resolution and blue resolution here. In the coarsest and finest resolutions, in total, we have 16 grid levels. Given a spatial position occurred during volume rendering, like this one here, we query each level of the grid for the 8 voxel grid corners that spatial position belongs to. Then we use trilinear interpolation between the feature vectors at those 8 corners to compute the output feature vector at this location, which is then concatenated together with the vectors from all the other levels and passed into the neural network. Next, we'll describe the weighted L2 loss that we use. In standard NERF, an L2 loss is used to supervise the neural radiance field. However, since the color distribution of HDR images can span many orders of magnitude, applying a standard L2 loss would cause bright regions to completely dominate the error and produce an image with muddy dark regions and low contrast. So following raw NERF, we use a weighted loss that more strongly penalizes errors in dark regions to align with how dynamic range is compressed by human perception. First, we apply a tone mapping curve on both the render estimate and then the noisy observed intensity. We can observe this as some sort of weight on top of the normal L2 loss. And following raw NERF, we use their implementation, which is a stop gradient on top of the result. For raw image post-processing, so after our NERF outputs the raw image values, we post-process them in the same way as a standard camera pipeline to convert the radiance values into tone-mapped sRGB images for display. Our post-processing algorithm matches the algorithms used in raw NERF. We use a color filter demosaicing to decompose the Bayer filter in front of the image sensor, and then we scale each color channel by the white balance coefficients of the camera, and then we convert the white balanced camera color space into sRGB, where we use the standard D65 lumen for XRGB on camera transform. Then we use gamma compression with the standard sRGB gamma curve. So now I'll go show some results. Unlike raw NERF, which is based on NERF, we use just the standard NERF as our implementation, and we also use a pure PyTorch implementation of instant GP since CUDA is quite difficult to work with. In the results here, you can see the raw test image on the left, the raw novel view in the middle, and an ablation study where we use L2 loss instead of the weighted loss that we talked about before. So you can see that our algorithm successfully denoises the raw images, and that our weighted loss is better than the L2 loss ablation, where you can still see a lot of haze and noisiness in the objects. More results here. More results here. That's all. Thanks so much.